So I think we can get started. Welcome everyone to this session about stream processing with Akka Streams. My name is Jacek Kunicki. I work at Software Mill. We're a remote software house based in Poland. So if after the talk you'd like to chat with me either about Akka Streams or remote work, feel free to catch me sometime during the conference. Two things before I start. First of all the code I'll be showing is available in a GitHub repository. There will be a link at the end of the talk, so you don't need to take notes at all. And secondly, the code I'll be writing is in Scala, but please don't be afraid and don't be scared even if you haven't seen Scala before. I think the code would be pretty straightforward. I'll try to explain the maybe not so straightforward things. So please stay here even if you don't know Scala. Okay, so what is stream processing actually? Well, perhaps a lot of you have heard about the concept. The general idea of stream processing is that you have a source of some kind of source of your data. We can call it a producer. You have a target place for your data, which we can call a consumer. And then you have a number of processing stages. And of course, the data flows from the producer through the processing stages up to the consumer. So you may think this is everything. But actually in Akka Streams, which is an implementation of Reactive Streams, we have some additional concept here. And if you've heard about reactive processing, reactive is basically about non-blocking. So that's the bottom line of reactive processing, not to block when you don't have to. So if you imagine such a stream processing pipeline, you can basically think about two kinds of scenarios. The first scenario is when the producer is pretty slow and the consumers or the processing stages are fast. So if you have a slow producer and a fast consumer, there is actually no problem because, well, the consumer will never be flooded by data, the producer will produce the data slowly, and the consumer will be capable of processing everything on time. But if you imagine the situation another way around, when the producer is really fast and the consumer is really slow, it can happen that the consumer will be flooded by data. I mean, it can get too much data, like much more that it's able to process, actually. Well, and perhaps it would somehow fail in this situation. So in the reactive streams concept, we have like an additional channel for communication. So the data flows from the producer through the stages to the consumer, but we also have something called back pressure. And in reactive stream, the back pressure is non-blocking. This is quite important. And back pressure is basically a way for a slower consumer to tell the producer that, well, how much data I can accept. So in Akka Streams, the back pressure is realized as signaling how much data can I get. Like, hey producer, give me n items of data because I know I will be able to process n items, for example, and nothing more. And this way, the consumer is able to limit the rate of the producer so that it doesn't get flooded by data and it's always able to process the data. So this is like a general idea. And of course, since Akka Streams is one of the implementations, they have their own terminology. So in Akka Streams, the producer is called a source, the consumer is called a sink, and all the intermediate steps are flows. Well, actually, source and the sink are also flows in the Akka Streams world, but let's just think as a source as a source, a sink as a sink, and all the intermediate steps as flows. If we combine them together, so link the various stages, they are called a graph. So and the graph is what is like the processing unit in Akka Streams. So there's really a number of technologies for stream processing. This is just a part of it. It's from my colleague's talk about small intro to big data. You can even notice that Akka Streams is not here. So how is Akka Streams different from all from the other solutions that we have? Well, first of all, Akka Streams is not distributed. If you heard of Spark, for example, and Spark Streaming, well, Spark is generally a distributed processing engine, and Spark Streaming is one of its parts, which is distributed. And actually, this may no longer be true because in Akka Streams, well, when you see the code, you'll see that will be like there are two parts. Well, first of all, what we'll be writing are only the recipes for data processing, but we won't be influencing how the data is actually processed. So what happens underneath? And in Akka Streams, you have something. If you have your graph defined, and then you have something that is called the materializer that is actually responsible for running the graph somehow. And up to recently, Akka Streams only had its default materializer, which is based on an actor system. But it turns out that there's going to be another materializer for Akka Streams based on Apache Gear Pump. Apache Gear Pump is one of the distributed stream processing frameworks there. It's actually an abstraction for other stream processing frameworks. So a materializer based on Apache Gear Pump has been announced for Akka Streams. So the statement that Akka Streams is not distributed may no longer be true. When defining the data processing with Akka Streams, we create some reusable building blocks. Which we have a DSL for creating the steps for our data processing pipeline. And it's important that when you create a graph, define the graph, everything is lazy. So until you actually run the graph, no processing happens anywhere. So you just have a DSL for defining your building blocks, and only when you want to run it, you need to have a materializer present. And when you execute some kind of run method on a graph, it's only then actually run. But when you define all the steps, nothing actually happens. So in our example project, we'll be dealing with some data stored in files. The files, each file would hold some lines with IDs and values, as you can see on the left. For every ID, there will be two lines with which either of them can hold a value or not. So there will be pairs of lines with valid values. There will be lines where one of them can be invalid or both can be invalid, but there will always be two lines for a single ID. And to make things, well, maybe not harder, but complicated, all the files are going to be gzipped. Then we want to do some intermediate processing on our data from the files. Here it's aggregation, and we'll be averaging the values by ID. Of course, when some of the values won't be valid for a single ID, we'll be using some dummy value to just mark that it was invalid, and ultimately we'll be storing our data to Cassandra. Well, of course, in our small case, we wouldn't need Cassandra at all, but this is taken from it's a simplified version of a real project we made, and we used Cassandra there, so Cassandra is here as well. And actually, if you had a real-world scenario where you wanted to do fast inserts to a database, Cassandra may be a good choice. Well, because one of its features is that it's really fast at accepting incoming data and inserting it. Okay, so let's get to the live coding part. I hope you can see it in the back. If not, there's plenty of room here in the front, so please don't be afraid to come here. Okay, so we have our CSV importer class, which has some configuration parameters that I will describe them later as I'll be using them. So in our file processing code, the first thing we may need to do is to, when we get a single line, we wanted to parse it somehow to our domain model. So we'll define a parseLine method, which would take a line, and the line will be a string. And we'll be processing the lines in some asynchronous fashion. So in Scala, if you want to declare that you're doing something asynchronously, you use a future as the return type. So future is basically a value, but deferred one. So you don't get it. You may not get it immediately, but sometime you get it. And we'll be returning a future of reading. Now, what's a reading? Reading is basically where there are two types of readings. We can have a valid reading, which has an ID and a value, as I said previously, and we can have invalid reading, which it is basically a marker class because it doesn't hold a value, well, because the value is invalid, but it holds the ID so that it's easier to do the aggregation and to process to average the readings afterwards. Okay, here we have a future block, which basically means that this will be executed in another thread. So this would be a non-blocking call. And what we want to do, well, the first thing, we are splitting the line by a semicolon. And the values are going to be our fields. Then we take the first field, we convert it to an int, and this is going to be our ID. Secondly, we take the second field, convert it to a double, and it's going to be our value. And now, well, we could just return a valid reading with the ID and the value. Well, but of course, this is a happy path for the lines that are correct, and of course, well, some of our lines may not be correct, so we need to handle this as well. And actually where it would fail if a line is incorrect is the to double, because there will be some kind of number format exception. So let's just surround it with a try catch. Well, we'll be catching everything. And here we'll do some logging just to know that there was an invalid line. And what we'll be returning here is an invalid reading with just the ID. So this is like a way to mark that one of the or both of the readings were invalid. And we're actually missing a file path here. So we'll complicate our method signature a little bit. Now this is, if you haven't seen Scala before, this may seem strange because we have two sets of parameters, but this is basically this is something called a partially applied function, and it means that if you call the parseLine method with only the file path, it would return a function that could then accept a line as a string. And this is just like it would help us to like put the method into into another method call which accepts a function. So we need the file path for the debugging purposes, and we need the line to do the actual parsing. Okay, so this is parsing the line when we have a string, but we don't want to read our entire files into memory because there may be a lot of them, there may be big, so we're gonna to stream the files. And actually, when we are streaming the files, we're basically processing a stream of bytes, and then what we want to do is we want to detect new lines in the stream of bytes to be able to split it into an actual strings. So our first building block of our processing pipeline will be something, we'll call it line delimiter. And here well, the method we defined before doesn't have anything to do with Akka Streams so far. Here is the first place where we'll be actually using the Akka Streams API. So as you may remember from the previous slides, the building block of a stream processing pipeline is a flow. And actually a flow has three type parameters. The first parameter is the type of the data that comes into the flow, so that comes into our black box. The second parameter, the out, is what gets out. And we also have a bit mysterious one called mat. This is a shortcut for materialized value. And materialized value is something that can be emitted from the flow to the outside world. Well, that's at least you can think of it as such. Because normally when flows, so when the building blocks of a stream communicate with each other, they don't emit any data to the outside world. They just communicate, well, between each other. But there is a possibility for a flow to emit something to the outside world, and we call it a materialized value. And actually, we'll not be using materialized values here at all, so we'll just be skipping it. So in our line delimiter, the input type would be a byte string, which is it's a type from the Akka Streams DSL, and it's basically a wrapper for, well, a string that's built of bytes. We'll also output a byte string, which only after we would convert to an actual string. And since we won't be using the materialized value here, we would use a type called not used. And not used is basically something that ties together the Java's void and the Scala's unit. Because Akka Streams also has a Java API, and well, in Java we have void, in Scala we have unit. They are a bit similar, but also a bit different. So the not used type is something that unifies it, so that the Java API is similar to the Scala one. So if your Java programmer is basically a void, if your Scala programmer is basically a unit. And for doing like Akka Streams has some built-in building blocks for common tasks, and actually for processing, well, for dividing data into frames, we have a built-in object called framing, and it has a delimiter method. And what it takes, well, if we want to divide our byte stream by something, then we need to define the separator. So here we'll just take the new line character. Then we define the maximum length of a line, where our lines are short, so 128 is a reasonable value here. There is one more parameter. It's called allow truncation, and it basically says what to do with a line that doesn't contain the delimiter at the all. So basically, if you have a file that doesn't have a new line character at the end, it tells Akka Streams what to do, because by default, if the allow truncation is set to false, it will fail on a line that doesn't have a new line at the end. But if we say set allow truncation to true, it will just process the last line without the new line character normally, so it wouldn't fail. Okay, so this is first building block, and as I said, it's lazy, so nothing actually happens here. It's just a recipe. What do we do with the incoming data? So the next step we're going to define is a recipe for parsing our files. So this is, well, we'll be using the flow type heavily because we'll basically defining the flows, the building blocks of our processing pipeline. So file parsing flow would be, well, its input type will be a file, the Java IO file. The output type will be a reading, either valid or invalid, because, well, we want to produce any type of reading from the files. And we're like ignoring the materialized value, so we say not used here. So previously we used the framing object, but normally when you build a flow with some input type, you just say flow of file, and then you have a number of methods. I'll just add some new lines so that it's a bit in the middle of the screen. So for when we will take our files, we want to stream them, and so for every file, actually we want to treat every file as a source of byte strings. So a source in terms of Akka Streams, so a producer of byte strings. So in this case, in the parse file stage, for every file we want to convert every file to a source of byte strings, and then then we'll do the actual parsing, and then we want to flatten all the sources. Like we'll have multiple sources of files, but what we want to emit from the flow is like a reading by reading. So that's called flattening. So basically we'll have a number of sources, which will be similar to the parallelism we define. And then for every source, we would like to take the output value and flatten it so the readings come out one by one. So for this, we have a stage which is called flatmap concat. And what it basically does, it changes it takes a number of sources and just flattens them so that the values are emitted one by one. So here we're going to have access to the files, so to every single file that gets into our flow. So since the files are gzipped, we'll create a gzip input stream, which would wrap a file input stream. Created from our file. And then we have a helper object called stream converters, to which we can pass an input stream, actually a function that returns an input stream. So here we have an anonymous function that just returns our stream that we haven't yet saved to a variable, so it's going to be a stream. We have the stream here, and what it actually is, when you check the type, so it's a source of byte strings. So basically, from every file there will be byte strings coming, but will be like we could flatten them then. So for every byte string that comes out from the files, first thing we want to do is pipe it through the line delimiter stage. So we have a stream of bytes and we pipe it through the line delimiter that we defined before. So now the output of the line delimiter is a byte string. Then what we want to do, as you may remember, we may have a header line in the file, so the name of the columns. So optionally, we may want to drop it from every file. Actually, we have a config parameter for that called lines to skip. So for every file, we'll be like passing it through the line delimiter to get single lines. Then we'll be dropping the first line because, well, it's a header line. And our line delimiter outputs byte strings, but we want normal strings that are accepted by our line parsing method. So we call the map stage, and map basically is like a map on a collection in Scala or Java. And actually, a byte string has a handy method UTF-8 string, which just converts it to string. So now we have our lines as strings, and what we want to do at the moment is convert every string line to a reading using the method we defined at the very beginning. And we want to do it asynchronously because, well, we want to preserve the order because the order of the line is important since they are grouped by the ID. But we want to do it asynchronously with some level of parallelism. So we have a map async stage. And it basically, well, it's also a partially applied function. It takes the parallelism level. And for our non-IO operations, we have a config parameter called non-IO parallelism. So this is for all the operations that don't require any resources like disk or database or something. And then we need to pass the actual function that takes a string and returns a future or something. So the function we defined at the very beginning, the parse line one, actually does this. Well, actually after applying the file path to it. So we'll say parse line. Here we call it with file get path. And what it returns is the function that takes a string and returns a future of reading. So this is the processing step. Once again, we're taking for every file. What we're doing is first we're applying our line delimiter to extract to split the byte stream by new line characters. Then we drop the configured number of lines, for example, the single one, which is a header. Then we convert every line, which is now a byte string, to a normal string that we want to work with. And then in an async fashion, we convert every string to a reading. So, and here we use the parse line method we defined at the very beginning. So having our readings, we are ready to, well, actually like a stream of our readings, we're able to group them by 2 and then compute the average. So this is going to be the next processing stage. It's going to be called compute average. Once again, it's going to be a flow. It would take a reading, and the output value would be a valid reading. So our average computation accepts any readings, be it valid or an invalid one. But what we want to output is a valid reading which has an ID and has a value. Of course, in the case when both the lines were invalid, we would emit just a dummy value. But we always want to emit something that has an ID and has a value. So we will be emitting a valid reading and not using the materialized value. So here, once again, our entry point is a flow of reading. So we have incoming readings, and what we want to do now is group them by 2 because every 2 lines share the ID and they may contain a value. And then what we want to do is process them, like again compute the average in an asynchronous fashion. But this time, since we already grouped the lines by 2, the order of computation doesn't matter. So previously we used the map async method. But it turns out that there is also another variant of it called map async unordered, and the difference is that map async preserves it executes asynchronously, but it preserves preserves the order of the results. So even if some result is computed faster, but it arrived later in the incoming stream, they will be output in order. But map async unordered doesn't care about the order of completion. It emits the value downstream as soon as it's computed. So of course it's faster, but sometimes you need to preserve the order, as we did in the previous stage. Here we don't actually care about the order because, well, we're just computing the average values and we don't need the order anymore. So here the parallelism once again would be this non-IO one. And what we get here is readings, because it's a sequence of or a list of 2 readings every time, because, well, there are a pairs of lines sharing the same ID. So what we want to do with the readings, well, since we're once again we're doing it asynchronously, so we'll wrap everything in a future. And the first thing we want to do, well, to compute the average, we want to extract the valid readings, because, well, the invalid ones don't have a value, so they won't be useful for computing average. So we'll take our readings, now do a collect operation, and basically for every reading that is an instance of a valid one, of the valid reading, we'll return it. So this is basically filtering, like filter with instance of, if you wrote it in Java. So we're basically filtering out only the readings that are instance of the valid reading. And we'll call it valid readings.
Is there no filter method by a name like filter?
There is a filter method, of course, but, well, it's basically a matter of style, because in the filter method you would need to use the instance of operator to check the instance of the class, and here some people may call it more elegant because you're using pattern matching here to detect the type of the object. Well, it's basically the same. So we could also say something like readings filter is instance of valid reading. So this would be the same. It's, as I said, it's only the matter of style. So now we're ready to compute our average. So if there are any valid readings, we want to extract value from them, the value from them. Value. Actually, let's check the type of it. Oh no, so the type doesn't match, yeah, because actually there is a difference because here the output type is still a reading, so we're getting a sequence of readings, and if we use collect, we'll get the actual valid readings. So well, thanks for this question, because this was something new for me. So we're going back to the collect variant. And we return this one. And now when we check the type, it's actually a sequence of valid readings. So since we only collected as a single type, the compiler knows that the type of the output collection will be a bit narrower. So now we're going to sum the values and divide them by the size of valid readings. Of course, this might be a bit of overhead when there was a single valid reading only, because then we could just return it. But for the sake of like simplicity, I don't want to write another like if branch here. Just let's say that we'll be like a bit not too performant when computing an average of a single reading. And otherwise, if the valid readings were empty, so there were none of them, we'll just return a dummy value of -1. And what we want to return here is a valid reading. And since we always had two readings as an input, we can just take the first of them and take the ID from there. And for the value, we'll be using the average that we just computed. So this is the average computation step. Once again, we take our reading stream, group it in groups of 2, so that we have the like two lines in a single collection. Then we filter it to extract only the valid readings, and then we compute the average. So the pre-final step will be to store our readings in the database. And this is going to be a flow that accepts a valid reading, since we only want to store valid readings in the database. The output value will be the output type will be the type that is returned by our Cassandra driver somewhere under the hood. So we don't really get into details, but this is a result set from the DataStax driver, and the materialized value is not used once again. So this is also pretty simple, because we have a flow that takes a valid reading. We can store the readings also in an async fashion, but this time, since this is an I/O operation, we'll use a different level of parallelism, and we have a configuration parameter called concurrent writes. So that we can adjust how many writes we do in parallel. Here we get a single reading. Well, and we have something called reading repository that has a save method. And the save method, well, it takes a valid reading and returns the future of the result set. So that's everything we need to know about it. Under the hood, it stores the value to a local Cassandra instance. So we're going to save the reading, and then we'll just do some logging. Just that our logs are not completely empty. The and then method is something it's called a combinator on the future, and what it basically does, it can intercept the future when it is completed, do some stuff, and return the original future. So here we like when the future is complete, we'll see whether it completed with a success or a failure, do some logging accordingly, and then return the original future. So that's all and then does. Well, and this is actually the whole flow for storing the readings. So now we're going to combine the building blocks we defined so far to build like a larger flow to process, which will be capable of processing a file and returning the result set. So we'll call it import single file. This is going to be a flow that takes a file, returns the result set, and we don't care about the materialized value once again. So now this is flow of a file. Sorry. And now it gets pretty straightforward, because we just use the via method to define the subsequent stages through which we want to pipe our data. So the first stage will be parsing the file. When we parse the file, we want to compute the average. And then when we have the average computed, we want to store the readings. And this is it. So this is so you can see that when you define your building blocks as variables or as vals here in Scala, you have a pretty simple DSL that just lets you combine them. And it's important that this is everything here is type safe, so that the compiler checks whether the types of the flows are fine. For example, if I switch the order, the compiler would say that, well, the compute average actually accepts a valid reading and not a reading, which is emitted by and not files. So in compile time, we already have some checks whether it would work or not, or actually whether it's legal to do or not. So this is almost our entire processing pipeline. So let's now define a method which would do the actual processing. So we have a configuration parameter for our import directory. We want to list files in the directory and then like put all of them, send all of them through our processing pipeline. So let's define an import from files method. And what it will return is a future, well, because it's everything happens in an async fashion, so it's non-blocking, etc. And the type of the future would be another mysterious type from Akka called done. And done is a bit similar to not used, because it's basically a unification of again of void and unit. And when not used indicates that we don't care about the materialized value of a flow, and done indicates that we don't care about the value that is emitted by after running the graph. So it basically says that, well, let's run the graph. Actually, our graph when it's run will have a side effect because it's going to write to the database. So we actually don't care about the value that will be returned. So we just care about the fact that it completes. And this is what done is for. And technically, it's just a unification of Scala's unit and Java's void. So we have our configuration parameter for import directory. We just list files, convert it to list from an array because, well, we have when we'll be creating a source from this sequence of files, an Akka Streams source, and it has a constructor that takes a list, not an array. So that's just for this. We'll store it in a variable. Let's make some more space here. Now we want to do some logging. We may want to measure the time it took to import it. So let's have the start time here. Now we're going to have multiple files that we want to send through our pipeline, but of course we wouldn't want to send them one by one. So we would also leverage the power of Akka Streams and of the parallel processing. So we would like to do a kind of load balancing. We would like to have an input to our graph that would load balance the files across a number of workers. So we would like to define a number of workers which would process the files in parallel and do some kind of load balancing. So there is one final stage a flow we need to define. We'll call it balancer. And so far we'll only stay with the type. So its type is similar to the import single file flow, well, because the balancer takes a file. It returns a result set and we skip the materialized value. Let's leave the implementation unknown for a second. But basically what it will be doing, it will be taking files, load balancing them between a number of workers, and then like merging the results of the load balancing and sending the parsed files one after another to the next steps of the pipeline. So now to run our entire graph, we'll need to start with a source, as this is a starting point for data processing. So we have a source object, and here we pass the files, the list we created. And what we want to do is like pipe it via our balancer, because the balancer will be taking care of actually executing the import single file flow. Well, not executing, but passing data there. And now this is the first place when we actually do something about running it. So we say run with, And well, we define the source, we define the intermediate steps. The only thing we have to define now is a sink. And in our case, as I said previously, we actually won't care about what is the value returned by our processing pipeline, because we only want to know that it has finished. So there is a handy string called ignore, which basically when you run the flow with sync ignore, it returns a future of done. So that's exactly the return type we want. Now we can and it returns a future, so we can once again use the and then combinator to do some logging. It would print the elapsed time and stuff like that. Okay, so now it's time to implement the load balancer itself. And here we'll use a bit different approach than we used previously, because we won't be using the built-in stages, so the methods that we can call on a flow, but we will build a simple processing, a simple graph from scratch using a graph DSL, which is another way in Akka Streams to define the processing steps. So we'll have a balancer graph, and now we're using the graph DSL to create it. What we get here as an implicit value is something called the builder, and builder is basically like our way to access the structure of the graph. So if we'd like to add a processing stage to the graph, we'll be using the builder instance to add the elements. We'll also use import the DSL for the methods of the graph DSL. You'll see them in a second. And now, as I said, we want two steps. Well, first of all, we want the balancing step that would just like take a file and choose a worker that is available, and then send the file to the worker. And then after we do the balancing, we have split our pipeline to like a number of sub pipelines. So and after they are done, we want to merge them back. So we have like a single input and a single output. But we have multiple pipelines in the middle, but we want a single output. So the first stage that we want to add will be called balance, and now we call the builder add, and we have a built-in stage for load balancing. Actually, we need to provide a type. Its type would be file, and the number of branches is one of our configuration parameters. It's called concurrent files. So we have the balancing step, and now which splits the pipeline. Then we want to merge the results back. So we'll need another stage called merge, which is also a built-in one. So we're going to add a merge here. The type parameter of the merge will be the result set, because that's the like final thing that comes from out of our pipeline. And the number of inputs to the merge block will be the same as the number of outputs of the balance block. And here, of course, well, there's no way to verify it at compile time, but this would actually be verified at runtime. So I'll implement one more step, like connecting everything together here. And now we'll be using the fancy arrows from the graph DSL. So now what we need to do is to basically iterate over our concurrent files, and for every like the number of times as specified in the concurrent files, we need to connect. We need to add like a connection between the balance stage. The data from the balance stage should be sent to import single file, and from there it should be sent to the merge stage. And the arrows you see here are from the graph DSL. So if you had a bigger graph, your code could look almost like a drawing. So with all the arrows connecting all the building blocks. And this what we have to return at the very end, because this is a graph, and every graph. I said at the beginning that actually source and sinks are also flows, or they are graphs actually. And every graph in Akka Streams has a shape. So, and a shape basically says how many inputs and how many outputs a graph has. So a source is a graph which has a source shape, which means it has only a single output. A sink shape has only a single input. And in our case, it would be a flow shape. And the flow shape has a single input and a single output. So just as we defined the flows before. But here we're just using the DSL. And the input of our flow would be the input of the balance stage, and the output will be the output of the merge stage. So this is the definition, and here and our actual balancer flow will be built from the graph we defined, just like that. And now the things here, all the connections between the stages, well, they are not verified at compile time, but they would be verified at runtime. When the graph is actually built and materialized, Akka, the materializer, is going to check whether actually the number of inputs and output matches, and if not, there will be an exception. Yes.
When you split up the input processing into these parallel branches, let's call them branches, I don't know what's the name, will you not overwhelm the writing to the database, because then instead of, if you scroll up,
Yeah.
when you scroll up you had these concurrent writes, and instead of it's just being concurrent writes, it's now concurrent files dot times concurrent writes. So it's a multiple of concurrent writes because it's happening in parallel.
Yeah, you're right. I haven't noticed that before. So the question was whether we aren't actually making more concurrent writes that we configured, and actually we are, because now when we since the store readings part, the store readings flow is a part of the import single file stage, which we are executing multiple times because we're using it within the load balancer. And yes, actually now the number of inserts would be concurrent files times store times concurrent writes. Yeah. Unfortunately, I don't have any prizes. If I had any, you would certainly get one, but sorry for that. Okay. Well, the last thing we need to do is to somehow call the method we just wrote. And so here we have our simple application. We have the CSV importer, and we say import from files. So let's now jump to our compiler and see what happens. So we're going to run SBT. And compile. And now we see there's a number of problems here. Well, there are actually two kinds of problems. First of all is that we are doing some manipulations on futures, and to do some manipulations on the futures, for example, to use the and-then combinator, we need something that is called an execution context, which basically is a thread pool that is used to execute the async operations. And in Scala, you need to be explicit about what kind of thread pool do you use. So it's actually a good idea, because every time you're doing some asynchronous processing, you should like think well what kind of processing it is, what kind of resources it may need, and what kind of thread pool do you want for it. Actually, you can make a workaround, which we will do, because there is something called a global execution context, which is defined. It's always in the application. And using a global execution context, especially for I/O operations, may not be the best idea, but for the sake of simplicity in our application, it would be enough. And the second kind of problem is at the very end, is that we want to run our graph, but as I said, our graph is only a recipe for data processing, and actually we don't know yet how to run it. And for this we need a materializer. And this is also, a materializer is an implicit parameter to the run method, or run with in our case. So here the compiler says that, hey, you need a materializer, so you need something that will actually run your recipe. So we're going to be using the actor system based materializer, so the default one. So let's just use an implicit actor system. Let's define an implicit actor system, so that basically an implicit value here says that, well, the actor system will come from somewhere when we create the class, and it will be there. It's an actor system, and actually an actor system, well, it has a thread pool that we will be able to use as the execution context. So actually, I lied before, because we won't be using the global one. We will be using the one from the actor system, which is even a worse idea in a real life scenario, especially for I/O operations, because the execution context from the actor system is responsible for all the communication between actors. So if you execute an I/O operation on the system on the execution context of the actor system, and if you block it by some accident, then the entire actor system may stop functioning. So don't do it in production. This is all only for simplicity. But this is the fastest way to obtain an execution context here. And here, since we have the run with method, which what was the shortcut? Yeah. So this is this shortcut that shows the implicit values. Sorry, that are needed. And you can see that. Let me try once again, that actually the run with method takes an implicit materializer. So that's what the compiler complained, actually. So if we need an implicit materializer, let's create one. It's an actor materializer, sorry. And it's a value. And here you can see that the actor materializer takes an implicit actor system, but we've already defined an implicit actor system and, in the class definition, so we'll have it here. And actually, where the actor system comes from is here. So in our application, we define an actor system for the application. It's an implicit value. So when we create a new instance of the CSV importer here, it is passed an implicit value as an implicit value. So it's provided there. So let's get back to the compiler. Really? Okay, I'm not sure whether I can do anything about it. Okay, something is wrong here. Okay, this should be fine, so I'll just... Okay, to co teraz? Ten mam wziąć? Czy? To już mogę wziąć ten do ręki. Okay, I need to use this one because it's recorded. So let's just not dig into what's wrong, but just get the working version. It's the same. I mean, it must be some kind of a minor mistake. Okay, so we'll say compile. Now it compiles. So we're ready to run it, and I have a Docker with Cassandra running here. We can connect to the SQL shell to see what's happening there. We have an Akka Streams readings table, which is now empty. So now we can try to run it and see what happens. Well, it may take a couple of seconds, well, depending of whether it's warmed up or not. And actually, if you go to the GitHub repository, I'll be linking at the end. Oh, it was faster than I thought. You also have the random data generator. So if you wanted to play with it yourself, you can try to generate a number of those random files. Then perhaps play with the different configuration settings to see how the parallelism levels influence the velocity and the processing speed. Okay, so that was for the live coding part. Of course, there is more, as usual. Actually, you have already seen how to implement your own graph with the graph DSL. So if you don't want to, if the built-in stages are not enough, you can build your own. You can also build your own flow. So, for example, that with some kind of other DSL, it may also be useful because, for example, you may need to do some stateful operations within the flow. It's also possible. I've actually written a blog post about it and contributed one of the custom flows to the Akka Streams contrib. So you may go to the blog and see if you're interested. So that's all I had today. Under the QR code, you have a link to a landing page which has links to GitHub, links to the blog post and some contact information. And vielen Dank für Ihre Aufmerksamkeit. And if you have any questions, I think we're almost done with the time, so you can ask now or catch me later. I'm here until the end of the conference.